3.3 is called the first derivative test. So not all critical numbers, remember we learned about critical numbers last time, it's when you take the derivative and you find the values where the derivative is equal to 0 or it just doesn't exist at all. And it's not the case that all critical numbers give rise to a maximum or minimum value. Last time we saw a bunch that did, but that won't always be the case. Because consider, for example, if we were going to graph y equals x cubed. If we were to find the critical number here, we would take the derivative. So that means we do y prime equals derivative of x cubed is 3x squared. And then we'd want to know, when does that amount, the 3x squared, when does it not exist? Well, it always exists. Or when does it equal 0? So to solve that, we divide both sides by 3. You get x squared equals 0. Take the square root of both sides. You get x equals plus or minus 0. But plus or minus 0 is just x equals 0. So this would be my critical value. So from what we did last day, you might think, oh, well, there's a maximum or minimum there. But let's graph this function, the y equals x cubed, and let's see what it looks like when we graph it. Y equals x cubed. Well, if we put 0 into that x, you get 0, 0. If you put 1 in there, you get 1, 1. If you put 2 in there, you get 2, 8. And same down here, if you put negative 1 in here, you get negative 1 coming out. If you put negative 2 in there, it gets negative 8. So you get something like this. Okay, so we found the critical number was at 0, which would make us think that there must be a maximum or minimum when x equals 0. But at that point, right here, this is not a maximum, and that is not a minimum. What we do call this is a turning point. So that value right there is a turning point. And I'm going to put in brackets just to emphasize this. It's not a max and it's not a min. I'll put not max or min. So a good question would be then, how do we figure out whether it is a maximum or minimum? When you get the critical values, it'd be really nice to know whether it actually is a maximum or minimum, or if not, if it's a turning point or if it's nothing whatsoever. How do we figure this out? Well, just let me do this. Let me sketch a little graph here that does have maximum minimums. So there you go. This right here is what? That point. That is a local maximum. And this point down here is a local minimum. Now, I know this is kind of obvious, but what would you say about the function right here? You would say that right here the function is increasing. And what would you say here? Decreasing. And what would you say over here? Increasing. So the point here is, if a function, you can show that it goes from increasing to decreasing, there must be a maximum. If it goes from decreasing to increasing, there must be a minimum. If you look at this one, what was it doing? It was going increasing to increasing. It was still increasing. There was no change. So if it doesn't change from increasing to decreasing or decreasing to increasing, then it doesn't have any extrema. But when it changes like this, there is going to be extrema. So what would be nice is, without drawing the graph, how to figure out whether it's increasing or decreasing. How are you going to do that? You're going to take the derivative. This is why it's called the first derivative. The first derivative will tell you whether your function is increasing at that point or decreasing. Because remember, if we were to draw your tangent lines over here, they're all positive. So when you take the derivative, they'll be positive. And then when you were to take the derivative over here, you'd get all the tangent lines are negative. So your derivatives would all be changed from positive to negative, which means it would be going from increasing to decreasing, which means there must be a local maximum there. I'm just going to get rid of all those lines. Okay, let's summarize that. The first derivative test. Let C be a critical number. So once you've found one of the critical numbers, or more than one of the critical numbers, but in this case we're just going to consider one of them, C, just like this was a critical number here of 0. And it's a continuous function. Remember, that's a function that you could draw without lifting up your pen, your pencil. The first derivative test says that if f prime of x, if the derivative changes from positive to negative at C, right, like increasing to decreasing, positive slope to negative slope, then there must be a local maximum. That's this case right here. Okay, the second one says, if f of x changes, so the derivative changes from negative to positive at C, well, that'd be this one, negative slope, decreasing, to positive slope, increasing, then there must be a local minimum there. And the last one says, if f prime of x, the derivative does not change sign at C, then f does not have a maximum and it doesn't have a minimum. So that would be this case here. If you were to look at the tangent lines here, you have positive slope tangent lines, sorry it's terrible, and then you have more positive slope tangent lines here. It never changes. So if you were going to do little sketches here, for the first one, when you have a maximum, right, there's a maximum right there, you have positive tangent lines, positive slope tangent lines, followed by negative slope tangent lines. If you were going to draw something with a minimum, like this, you would have negative sloped tangent lines, followed by positive sloped tangent lines. And then if you have no maximum minimum, it might look like this. So in this case, you have positive tangent lines, followed by positive tangent lines, or it could look like this, where you have negative tangent lines followed by negative tangent lines. Okay, we're going to skip this first derivative test for absolute extreme values. We're going to skip that, and we're going to work with this first derivative test for a little bit. So let's go to the back. Find the local maximum and minimum values of f of x equals x cubed minus 3x plus 1. So the first thing you want to do is you want to find the critical numbers. Sometimes I'm going to say critical numbers, sometimes I'm going to say critical values. It's the same thing. Critical points, I think some people say. So the critical numbers, how do we do that? We take the derivative. So we find f prime of x, which equals 3 comes down, 3x squared, minus 3, and that's just a constant, so we're done. Then you want to know, when is it that this amount, the derivative, 3x squared minus 3, when does it not exist? Well, it always exists. Or when does it equal 0? So let's do that. You could do this in two different ways. You could factor out a 3, or you could move the 3 over. What the heck, I'll factor out the 3. It's not usually the way I would do it, but I'm going to do it this time. Factor out a 3, you're left with x squared minus 1 equals 0. You can factor this. That's a difference of squares, so it'd be x plus 1 and x minus 1 equals 0, which means x can either equal negative 1 or x can equal 1. So these are our critical numbers. So now what we're going to do is we're going to take a look at the value of the derivative in the intervals between and beyond these points. How are we going to do that? It's another wiggle graph. So wiggle graph, negative 1, 1, and I want to know the value of the derivative in each of these intervals here. So we're going to test these intervals here, but be careful where we're testing these intervals. I'm going to write this here. Test intervals in f prime of x. You're not plugging them into f of x, you're plugging them into f prime of x. You want to know whether the derivative is positive or negative here, positive or negative here, positive or negative here. You know what the derivative equals here. What's the derivative equal right at 1? It equals 0. What's the derivative equal right at negative 1? It equals 0. So we just got to figure out these ones. Again, I think it'd be smart to use the factored part of this, so probably right here. And you don't even have to worry about the 3 because you could divide both sides by 3. So let's get rid of the 3 and just use this right there. Alright, so let's try a number bigger than 1. I'm going to use 100. What the heck? I can use anything I want. 100. 100 plus 1, positive. 100 minus 1, positive. Positive times positive is positive. So this ends up being positive. Remember, I'm not actually interested in whether this equals 0. I just want to know whether it equals a positive amount or a negative amount. This equals positive. So what this is telling me is that in this region, when in our function, for all the x values greater than 1, what does it tell you about the function? It tells you that the function is increasing. So I'm going to write increase right there. Okay, let's try between negative 1 and 1. Well, come on, let's be sensible. Let's try 0. 0 plus 1, 1. 0 take away 1, negative 1. 1 plus negative 1, negative 1. So this is negative. What's that mean for the function itself? It means it's decreasing here. Okay, something less than negative 1. Let's put negative 5 in here. Negative 5 plus 1, that's negative. Negative 5 minus 1, that's negative. Negative negative makes positive. So for this part, this interval down here, the function is increasing at this part. Great, now we want to find the local maximum and minimum. So the next thing you do is you take a look here. It goes, the function's going from increasing and then decreasing. What's that mean happens right here? At negative 1, there must be a maximum right there. So let's write that down, that there's going to be a maximum right there at negative 1. And then it goes from decreasing to increasing. Decreasing to, oh, at 1, there must be a minimum. We've done it. We've found the maximum. We've found the minimum. Now, let's say we want to know the value of the maximum. Like, it's great. I know there's a maximum at -1, but I want to know how big the maximum is. So how are we going to figure that out? Well, you're going to plug -1 into what? Don't plug it into f prime of x. You know what you get when you plug -1 or 1 into here. You get 0. That's not what we want. We want to know in the function itself, if you have an x value of -1 or 1, what's the y value? What's the output value? So you're going to plug those values into the f of x. So we have to do two things. We have to find what f of -1 is. We have to figure out what f of 1 is. Okay, so we plug -1 into here. -1 cubed minus 3 times -1 plus 1 equals -1 cubed is -1, -3 times -1 is 3, plus 1, those cancel, and you're left with 3. If you put f of 1, means you plug 1 into here, you get 1 cubed minus 3 times 1 plus 1. That's 1 minus 3 plus 1. What's that equal? -1. Okay, so what we've just found out is that there is a maximum of 3, that's the biggest output or the biggest y value, when do you get that? When x equals -1. And we have a minimum value of -1 when do you get that? When x equals +1. Okay, you're going to do this a lot in this course, so you really want to make sure that you understand this concept. Let's try another one, a little more difficult. Find the local maximum and minimum values of f of x equals 2x minus 3x to the 2/3. So basically you're going to do exactly the same thing. It's just a little bit harder derivative here. So we got to get our critical values. How do we get the critical values? We find the derivative. So the derivative of 2x is 2 minus, now careful here, the 2/3 comes down and we multiply by 3. What's 2/3 times 3? Well, that's 3 over 1. Those cancel. You're just left with 2. So we have 2x to the, all right, we have to drop this 2/3 down by 1. So that equals -1 over 3. Now when you're doing this first derivative test, it's good to get this with a common denominator. So first of all, let's write this. This is 2 minus, in the numerator we have 2, and the denominator we have, this is a flipping negative, so it's going to come to the denominator. You have x to the 1/3, which is same as the cube root of x. And then as I said, we like to get a common denominator, so this is over 1. Our lowest common denominator is the cube root of x, so you'd need to multiply top and bottom here by cube root of x. So you're going to get 2 times the cube root of x minus 2 all over the cube root of x. And why don't we go ahead and factor this right now. So in the numerator here, you could factor out a 2. So you get 2 and then the cube root of x minus 1 all over the cube root of x. Okay, so that's our derivative in factored form, and what we want to know is, when would this equal 0, or when does this not exist? So when this does not exist when the denominator, cube root of x, equals 0. When's that? Well, if you cube both sides, in order to get rid of the cube root, you cube both sides, you're going to get x equals 0 cubed, which is just 0. So that's one of our critical values. X equals 0 is one of our critical values. The other thing we have to ask is, when would this equal 0? Well, this would equal 0 when our numerator equals 0. So we have to look at 2 times the cube root of x minus 1 equals 0. You could divide both sides by 2, and then this will just be gone. You could just cross it out. So now we only have to deal with this. So I'm going to move the 1 over. I get cube root of x equals 1. And then I'm going to cube both sides, cube, and I end up with x equals 1. So we have two critical values, 0 and 1. What are we going to do with those? We're going to put them on our wiggle graph, 0, 1. And what we're going to do now is we're going to check the intervals. Where are we going to test them? We're going to test them in the derivative, and I would recommend you do it right here in this factored form right here. All we want to know when we do this is whether it's going to be positive or negative. So let's start with something up here. By the way, you're taking a cube root of something, so if you want, it might be easier to take something that you can get a perfect cube of. Like I can use 8, If I put 8 in here, I get the cube root of 8, which is 2, take away 1, which is 1, times 2, it's 2. So the whole top part here is 2, or it's a positive number, is all you really care about. On the bottom, you'd have the cube root of 8, which is 2. So it's positive as well. Positive divided by positive is positive. So this is going to be positive. What's that mean about the function itself? It means it is increasing. Okay, let's go down here next, because this is going to be a bit ugly. Let's go down here. Let's pick negative 8. Actually, let's put negative 1. You can take the cube root of negative 1. Let's do negative 1. So on the top, the cube root of negative 1 is negative 1. Take away 1 is negative 2. And negative 2 times 2 is negative 4. So it's negative on top. On the bottom, cube root of negative 1 is negative 1. Negative. Negative divided by negative is positive. So this is also going to be increasing. Now you can probably guess, but let's just make sure. Let's put, well, you could put something like an eighth in there if you want. If you put 1/8 in there, the cube root of 1/8 is 1/2. I mean, you're welcome to use a calculator here. If you're like, well, I can't do that, I don't know, that's fine. Put 0.5 in here and use a calculator if you want. But I'm going to use 1/8 because I can take the cube root of 1/8 in my head. So I get 1/8, the cube root of 1/8, which is 1/2. Take away 1. Well, 1/2 take away 1 is negative 1/2. And negative 1/2 times 2 is something negative, right? 2 times a negative is a negative. So I know I'm going to have a negative on top divided by the cube root of 1/8. Remember, that's what I plugged in here was 1/8. Cube root of 1/8 is 1/2, which is positive. So I have a negative divided by a positive, which is negative. What's that mean? That means it is decreasing right here. Okay, now we can say whether it's maximum or minimum. It goes from increasing to decreasing here. Well, increasing to decreasing means maximum right here. It goes from decreasing to increasing here. What's that mean? It means minimum here. What if we want to know what the values are of the maximum minimum? Then you got to plug those values, the 0 into 1, into, we're going to plug them in, into here, back up there. So let's quickly do that. We need to find out what f of 0 is and f of 1 is. Those are nice numbers, it should be quick. F of 0 means 2 times 0 minus 3 times 0 to the 2/3. Well, that's 0. 0 to the 2/3, 0 to anything is 0, so 3 times 0 is still 0. So you have 0 minus 0, which is 0. F of 1, well, that's 2 times 1 minus 3 times 1 to the 2/3. 2 times 1 is 2. 1 to the 2/3, 1 to anything is just 1, and 3 times 1 is 3. So we have 2 minus 3, which is negative 1. So to summarize, we have a maximum of 0 when x equals 0, and we have a minimum of negative 1 when x equals 1. And by the way, sorry, I should have done this before. All these things in here I've written here where it says max and minimum, they should all say local, 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 local. When we use the first derivative test, you're going to find local maximum minimum. You can't say whether it's absolute unless, which brings us back to the first page, unless this is possible. So if you want to be able to say with the first derivative test that it's an absolute extreme value, then what needs to be the case is that the derivative is positive for all the x's less than c, and the derivative is negative for all the values greater than c. In that case, you can say it's an absolute maximum value. And if the derivative is negative for all the x's less than c, and the derivative is positive for all the x's greater than c, then you could say that f of c is the absolute minimum value. Okay, but to tell the truth, this won't happen so much. Almost always what you'll actually be doing is just this first derivative test right here, but sometimes they might ask you to find the absolute extreme value in this way. So why don't we do that with one question right here? So the steps start out pretty much the same. You got to find those critical values again. How are we going to do that? We're going to take the derivative. So f prime of x equals, derivative of x is just 1. 1 over x, that's the same as x to the negative 1. So the derivative of that would be negative 1x, or just negative x, to the negative 2, which is the same as 1 minus 1 over x squared. And remember we said we like to get common denominators for our derivatives. So let's make this 1 over 1. Our common denominator is x squared. So you have to multiply top and bottom by x squared. So you get x squared minus 1 all over x squared. What do we have to do now? We have to ask ourselves, when does this not exist? And this does not exist when the denominator, x squared, equals 0. When's that going to be? Well, that's going to be when x equals 0. And then the other thing we have to figure out is when would this equal 0? And when this would equal 0 is when the numerator, x squared minus 1, when that equals 0. So you can factor this side, you get x plus 1, x minus 1 equals 0, which means x equals negative 1 or 1. So you have three critical values here. So now what you're going to do is you're going to do your wiggle graph. But we're going to notice something here. We're going to put on negative 1, 0, and 1. But what you notice here is that x has to be greater than 0 here. So all this part of the graph, you don't need to look at. This isn't actually part of the function. The function is only bigger than 0. So you only have two intervals that you have to worry about. You have to worry about the interval greater than 1 and the interval between 0 and 1. So let's do that right now. We're going to test these two intervals, and we're going to test them right... Oh, actually, you know what I should have done? I should have factored this before I did the rest of my work. So I should have made it x plus 1, x minus 1, all over x squared. That would have been the best thing to do right there. That's where I'm going to test it, right there. So let's try 2 first of all. 2 plus 1, I know it's hard to see, but 2 plus 1 is positive. 2 minus 1 is positive. 2 squared is positive. Everything's positive, which means this is positive. It's increasing. If I put something between 0 and 1, well, let's put 1/2. 1/2 plus 1 is positive. 1/2 minus 1 is negative. So we have a positive, we have a negative, and it's divided by 1/2 squared, still positive. We only have one negative, which means it's going to be negative. That means it's decreasing. Now, this is going from decreasing to increasing. So what does that mean? It means it's a minimum. But this meets the criteria we were looking at over in this first page, where we said if the derivative is negative for all the x's less than c, and the derivative is positive for all the x's greater than c, then we can say it's absolute value. And you see that's the case we have here. For all the values we're interested in this function, because we're not interested in these ones we've crossed out, for all the ones less than 1, they're decreasing. For all the ones greater than 1, they're increasing. So this is a situation where we could actually say this is an absolute minimum. You know what I'm writing, absolute minimum. Okay, last thing, let's figure out what the value is of that. So we would have to plug 1 into our function. We have to find what is f of 1. So that would be 1 plus 1 over 1, which means 1 plus 1, which is 2. So what we have is an absolute minimum of 2 when x equals 1. And we are finished.
Feed until you're taken and tossed, and when I'm breaking it off, there's no denying the fact it's wrong, cause you got a man who probably playing his part, you probably breaking his heart, he trying to figure the reason you're gone. Is it cause he's superficial, or is he too